we're going to get into week 13. So week 13 goes over section 5.4, and hopefully we get into 5.6, but quite honestly, I don't think that's going to happen. I think we're going to get to 5.4 and 5.5 this week. But starting with 5.4, I wanted to start by just considering three different graphs. We've got the graph y is equal to x, y is equal to 3 over 5 times x, and y is equal to 1 over 5 times x. Obviously, in these three examples, what we've got is the slope is decreasing, right? Lower and lower slope. Now, I want to ask a question. If we consider 0 to 5, so 0, 1, 2, 3, 4, 5, if we consider the area underneath this line, underneath our graph, up to the x-axis, so from our x-axis up to our graph, for x between 0 and 5, what's the area underneath each of these curves, each of these lines? Well, it might not be obvious right away, it might not jump out at us, but what we've got hidden inside of each of these is a triangle. So sketching this out really quick. We've got our line, y is equal to mx. Now we're going over by units. So our y values associated accordingly, right? And what we're trying to do, what this question is asking, is for us to find this area. So if we get rid of all the extra stuff, get rid of the graph, what we've got is a triangle that its base, one leg, is a length of 5, and the other leg is a length of whatever the slope is times 5, right? We know how to find this area, right? This area let's relabel these legs. Let's call this A, let's call this B. The area is going to be 1/2 A times B. Agreed? Well, plugging in what we know, we've got 1/2 5 minus 0, because that's the length, right? That's what we said. This went from 0 to 5, times whatever that height is, minus whatever this bottom height is, which is just going to be 0. So m5 minus 0. Agreed? Well, if we generalize this even further, this is x, isn't it? It would look something like this, right? So what I'm trying to say is, in the case of y equal to x, we know our two legs are 5 and 5 long, right? In the case of 3 over 5x, our legs are going to be 5 by 3. And in the last case, they're going to be 5 by 1. So our area under each of these different triangles will be 1/2 25, 1/2 15, and 1/2 5. Now, we can generalize this a little bit more. Well, before we get there, I just want to point out what this comes out to be is 1/2 25, so 12.5. 1/2 15, so 7.5. 1/2 5, so 2.5, right? Notice as the slope decreased, the area decreased, right? So it seems like what we're hinting at might be that the derivative is somehow related to the area underneath the curve. Smaller derivative implied smaller curve, smaller area. So there might be some sort of a relationship going on here, right? Now, moreover, we can generalize this a little bit further and notice that, just like I wrote on the board, the area function is m times some length squared divided by 2. Now this L, in this case, is a fluke of the math. It just happens to be that we can think of it as the leg squared. It's not an exact thing. And the reason why that happens will show up later. But this should get us thinking. This thing kind of looks like an integral, doesn't it? It kind of looks like the integral of mx with respect to x. Agreed? That's because it is, actually. What's happening here, as we'll see in a second, is that the integral is going to tell us something about the area under a curve between two given x values, the function and the x-axis. And since the integral tells us something about the area, it also tells us that the area and the derivative, or the slope, are both also going to be somehow related. So with this as a motivation, what we've got, or what we found up here, is called a definite integral. What we're seeing, what we're observing, and kind of hinting at through all of this. It's called the definite integral. And what the definite integral says is you want to integrate a function from a to b. Okay, so what does that mean? We're going to see in a couple minutes that what that means is you're going to take the integral of your function, then you're going to evaluate that integral at b, and subtract from it whatever it evaluates out to be at a. More of this will become obvious in a little bit. But for right now, let's consider an example. Another triangle and another line. The area underneath this line from 0 to 2 is equal to the integral of 2x dx from 0 to 2. And we can check this pretty easily, right? So we know the area of this triangle is going to be 2 times 4 times 1/2. That's going to come out to be 4. So the question now becomes, what the hell are these subscripts and superscripts doing? What's this 0 and 2 at the top and bottom of the integral sign doing and telling us? Well, it's pretty clear just from this picture that it's telling us something about where we're looking at. So it tells us something about the area between 0 and 2. But more than that, what is it doing? Functionally, how do we evaluate this thing? That is where the fundamental theorem of calculus comes in. So the fundamental theorem of calculus tells us that the integral of a function with respect to its variable from a to b is equal to whatever that integral evaluates out to be, evaluated at b, minus that evaluation at a. Now, just some details on the anatomy. A here is called a lower bound. B is called an upper bound. And that makes sense, right? Because we're talking about boundaries of doing stuff. A is the lowest boundary. B is the highest boundary. So lower bound, upper bound. And this result is, again, the fundamental theorem of calculus. So I'm going to explain more of this later in the material, but this is just a way of comparing what's going on. What we're saying here is that if we take a rectangle underneath our curve and say the right hand of that rectangle, the right side, sorry, I'm looking at the board doing right and left, right? So the right side of our rectangle, left side, because I flipped that, yeah. The left side of our rectangle is going to be the height of our function at some n value. And then we're going to say, all right, cool. The width of our rectangle is going to be delta x. This thing is going to have area smaller than what's actually under the curve from m to m plus delta x. Now, if we go the other way, and we say the right-hand side is the height of our function, that's going to be a little bit larger than the area under our function. And this is what the fundamental theorem of calculus uses to prove everything. It says, all right, evaluate f of m times delta x. That thing's going to be smaller than the area. Capital M is lowercase m plus delta x. So f at capital M times delta x is going to be larger than the area. Divide things out, take limits, and we find that our function is the same size as the derivative of the area. It's the same value. That's what we're saying here. So because of that, we get the fundamental theorem of calculus. This is just one proof for it. So again, the fundamental theorem of calculus, the integral of a function from a to b with respect to its variable x, that thing is going to be equal to whatever our function evaluates out to be under the integral calculated at b minus the same thing calculated at a. So going back really quick, back to this example. So what we're saying then is that the integral of 2x dx from 0 to 2, this thing, what we're going to do is first ignore the bounds. I'm going to just calculate it like this. So what I'm saying here is ignore this notation for a moment. just do this part. Well, this we know what it comes out to be. This is going to come out to be 1/2 2x squared. And in a minute, we're going to evaluate it from 0 to 2. Well, we can simplify it to get x squared from 0 to 2. Okay, now this one-sided right-hand square bracket, it's doing the same thing as the 0 and 2 is over here. All we're doing is saying, hey, do this integral and then calculate it at, evaluate it at 2 and subtract from that whatever evaluates out to be at 0. So what does that look like? That's going to look like two squared minus 0 squared, or 4. Lo and behold, that was in fact our answer, right? So, just some more details on what all is happening here. Generally, just pro tips for what to do. First thing you're going to want to do is calculate your integral. That's the very first thing you're going to want to do. And then apply your bounds. Now, looking at all of this, you might ask, what about C? Where is that C? Well, you're right, good call. We do need to have that C in there, but notice what happens when we take the difference. That C ends up washing out. And because it washes out, it just reduces to the integration evaluated at B minus the integration evaluated at A.
So when you're solving it for this specific instance, is it okay to just not add the C? Or?
Yes.
Okay.
Yes, we can totally, in this case, ignore the C because it just washes out in the end. Which is kind of convenient, actually. Now, some properties of the definite integral. The first few are pretty much the exact same, right? First three are. Or I guess the first two, I should say. The third one, things change a little bit. The third one says you can break it up. To give an example of what we mean, let's say we have the integral from 0, let's say from 1 to 3 of a function. Well, this thing is going to be equal to the integral from 1 to 2 of that function plus 2 to 3 of that function. Now, if we stop and think about this, this makes sense because what we're doing is saying we got some function. We're going to calculate the area, in this case, from 1 to 3. That's all of this. Now, doing the same thing from 1 to 2, that is this half, and from 2 to 3, that is this half. Well, if we add those two areas back together, we get the original area, right? So that's where this third property is coming from. This fourth property says if you evaluate an integral from a point to that same point. So they use A. I'm going to use a specific example. Let's say let's integrate. Let's integrate 2 with respect to x. Well, this thing is going to come out to be 2x from 1 to 1. If we're integrating from 1 to 1, if we're integrating 2 with respect to x from 1 to 1, then we're going to get 2x evaluated from 1 to 1. So 2 evaluated at 1 minus 2, x evaluated at 1, it's 2 minus 2, or just 0. So that's where this fourth property is coming from. And finally, this last property is saying, let's imagine we want to integrate from 0 to 1. This is going to come out to be 2x from 0 to 1. That's going to be 2 evaluated at 1 minus 2 evaluated at 0. This is going to come out to be just 2. Now, what if we flipped those bounds? So from 1 to 0, 2 dx is equal to 2x evaluated from 1 to 0. This is going to be 2 times 0 minus 2 times 1, which is equal to -2. What we're saying here is the order with which you write your bounds matters. It tells you the direction of integration. It tells you you're integrating starting at 0, going to 1 in this case. And here it says you're integrating from 1, going to 0 here. So in a sense, in that way rather, the integration depends, the result of the integration depends a little bit on the direction, right? There's some sense of direction going on here. So conveniently, we could, and this is useful from time to time, rewrite an integral from a to b, f of x, dx is equal to negative from b to a, f of x, dx. We could just flip the order of integration and apply negative sign out front. And this is, like I said, convenient from time to time. I wish I had an example right off the top of my head, but unfortunately I do not. Okay, so as an example, let's consider the function x squared minus 1. We want to know the area underneath that function from 1 to 2. X squared minus 1. So what does it look like what we're doing? What we're doing is we're finding this area here. Another way to think of it is we're finding the area of this weird triangle looking thing. It's not quite a triangle because it's got a curve in it, but it kind of looks like one. Well, thinking back to an algebra course or a geometry course, we don't have an equation for this area. But we do have the integral, and the integral can be used to find this area. And that's why we care about this thing. That's one of the reasons why we care about this thing. So evaluating this thing, what happens is we're going to get 1 over 3 x to the third minus x, evaluated from 1 to 2. So solving it now, we're going to get 1 over 3 evaluated at 2 cubed, right? Minus 2. This thing minus 1 over 3 x cubed evaluated at 1 minus 1. From here, we can do the rest of the algebra, right? We're going to get 8 over 3 minus 2 minus 1 over 3 minus 1 minus the quantity 1/3 minus 1, dropping our parentheses and distributing that negative through. This is going to come out to be 8 over 3 minus 2 minus 1 over 3 plus 1, and we can do the rest of the algebra. So, jumping forward and looking ahead, they do the same thing, right? They evaluate the integral, and then they apply their bounds. When all is said and done, answer should come out to be 4 over 3. All right, so now we've got another case. We've got this case of the integral from 0 to 1 of 4t plus 1 quantity squared dt. Okay, we have two different methods we can use here. We could go for u sub, or we could just go ahead and expand out this term. For the sake of brevity and just completion of the problem, I'm going to say let's go ahead and expand it out. Let's not use u sub. So when we expand it out, what we're going to get is the integral from 0 to 1 of 16t squared plus 8t plus 1 integrated over t, or integrated with respect to t. And now, doing all the math, this is going to come out to be 16 t cubed over 3 plus 8t over 2 plus t evaluated from 0 to 1. So doing that math now, this comes out to be 16 1 cubed over 3 plus 8 times 1 over 2 plus 1 minus 16 times 0 cubed divided by 3 plus 8 times 0 divided by 2 plus 0. Well, all of these terms drop out on the right. So what we're left with is 16 over 3 plus 4 plus 1. And this thing should come out to be 31 over 3. So looking back and just checking everything we've done, what we found is the area under this weird shape. It's going to look something like this. And that area comes out to be, after we do all the integration, 31 over 3. Now notice they applied U sub here. And they still got the same answer. The point of this is to say that as long as what you're doing is mathematically correct, doesn't matter. You could use U sub, or you could expand things out. But in either case, you're going to get the right answer. Now, just as an example of a couple problems where you would probably want to use U sub, or you have to use U sub rather, let's look at A first. A is the integral e to the 2x. You can't solve that. Not without using U sub. Or multiplying by that 1, right? One over x dx, that's going to give us an ln. And here, this is just going to be a power rule, right? But as we do and evaluate each of these problems, we're going to follow the same methods. So, looking at that first integral, you're integrating from 0 to 3 of e to the 2x dx. That's going to come out to be, let me write this out on the board. Zero to 3, e to the 2x. This is 1/2 e to the 2x, evaluated from 0 to 3, which is going to give you 1/2 e to the 6th minus 1. For those who are looking at this and wondering where I got that 1, e to the 0th power comes out to be 1. Now, in the second example, we had the integral from 1 to 2, 1 over x dx. This is going to come out to be the ln of x, evaluated from 1 to 2, This is going to be the ln of 2 minus the ln of 1, which is just equal to the ln of 2. There's two different ways we can see that. We could either bring these two ln's together. We would have the ln of 2 divided by 1, or we could remember that the ln of 1 is 0. So either case, we're just left with the ln of 2. And now, in this final case, we have the integral from 1 to 4 of 3 times the square root of x dx, right? This is going to come out to be 3 times 2 over 3, x to the 3 over 2, evaluated from 1 to 4. These 3's are going to cancel. So we get 2x to the 3 over 2 from 1 to 4. And the rest is just algebra. Now, a point on notation. I have used two different forms of notation to denote how we're going to take the difference. I've used a square bracket from A to B. I've used a bar from A to B. The book has, on two different occasions, I think now, used a rounded bracket from A to B. All of these are just different ways of saying the exact same thing. We use them for different reasons based on what's around, right? We have a lot of square brackets and rounded brackets, we generally go to the bar. If we're using a lot of square brackets, we might use the rounded bracket, but this is a lot less common. Generally, it's going to be one of these two notations. The book, however, like two examples that I've seen so far, like here, they've used the rounded brackets. So just as a point, there's a couple different notations you might see for the same exact thing. It's just going to be a contextual observation. All right, so what about the absolute value? Really haven't talked much about integrating this. There's a good reason why we haven't. Why haven't we, up to this point, talked about integrating this? It's because this doesn't actually mean anything. Because what's happening here, what this absolute value sign really means is that it's a piecewise function of a particular type. This thing is actually x whenever x is greater than or equal to 0, and negative x whenever x is less than 0. So really, this just chops up our function into two different parts. So we can't actually do this. But we could do this. We could integrate the absolute value from -1 to 1. And the reason why is because we can say, all right, well, this thing is like saying from -1 to 0 of negative x dx plus 0 to 1 of x dx. And now we can integrate. Because of symmetries, this is going to turn into 0, but to give you an idea of how we're going to approach this problem, we first need to understand this. Okay, so having said that, now, the absolute value of 2x, is it plus 1 or minus 1? This is going to be 2x minus 1 whenever 2x minus 1 is greater than or equal to 0, and negative 2x minus 1 whenever 2x minus 1 is less than 0, right? Great, that means we need to solve some inequalities now. That sucks. But we can do it. It's not going to take long. First inequality we need to figure out is when is 2x minus 1 greater than or equal to 0? Adding 1 to both sides, 2x greater than or equal to 1, dividing x from both sides, dividing 2 from both sides, x is greater than or equal to 1/2. Sweet. Now we can break up this integral. Now we can say this, the integral from 0 to 2 of the absolute value of 2x minus 1 dx is equal to the integral from 0 to 1/2 of negative 2x minus 1 dx plus 1/2 to 2 of 2x minus 1 dx. And that we can evaluate. So really quickly, just looking at what's happening here. Looking at the graph of this absolute value, we can kind of see what's happening. We can see, all right, cool, we've got a discontinuity in the derivative, right? That derivative suddenly just jumps. We go from a negative slope to a positive slope. We've got two different functions here. This thing's doing something ugly. On the left-hand side, it looks like negative 2x minus 1. And on the right-hand side, it looks like 2x minus 1. Where does that jump happen? Well, that jump happens whenever x is equal to 1/2. So we have to break it up into these two parts. To say, all right, this first part looks like the negative slope part. This right part looks like the positive slope part. Now, another point on this doesn't happen very often, but it does happen enough that we need to know about it. If it was something like x squared, don't worry about it, you don't need to do this. We only have to do this in this particular instance because of the absolute values. There are other functions that require this, but we, right here, right now, only have to do it because of the absolute values. So jumping ahead and looking at the solution, you make the same observation, right? That, hey, the absolute value of 2x minus 1, it's a piecewise function. It breaks up according to 1/2. Right? So that means the integral from 0 to 2, since 1/2 is in between 0 and 2, well, because that happens, we have to break it up according to the two pieces of this function. Anytime you have a piecewise function, you need to worry about this. And that's because what a piecewise function does is it says, let's stitch these two things together. Because we're stitching them together, you get some weird behaviors. Things change, and you can't just integrate all the way through the same way. One part behaves different from the other part. That's all we're saying here. So, after we break up our integral into the two parts, we can evaluate it just like we normally would. And once we do the algebra, it comes out to be 5/2. So, one application of this definite integral is with marginal analysis. So we might have a marginal function, marginal cost, marginal revenue, profit, whatever. We want to find out what the revenue function is. We want to find out what the cost function is. We want to find out whatever, right? We want to know what happens in that time frame. We can use the integral to do this stuff. Okay, so what we want to do is we want to find out the change in profit when the sales went from 100 to 101 units. And we're given the marginal profit for a product. We want to know the change in stuff, the total change. So we're told dP dx, profit as a function of the number of products sold, right? This thing is equal to negative, stupidly long decimal, 0.0005 x plus 12.2. Okay, we want to know what the change in profit is when sales increase from 100 to 101. First thing we want to notice is that dP dx integrated with respect to x is going to give us our profit function plus a constant, right? So if we integrated this thing from a to b, dP dx integrated with respect to x, that's going to give us profit at b minus profit at a. Well, I do declare that's the change in profit. So using this observation here, we're going to integrate this from 100 to 101. Integral from 100 to 101 of negative 0.0005 x plus 12.2 integrated with respect to x. This is going to come out to be negative 0.0005 x squared all over 2 plus 12.2 x from 100 to 101. So now we calculate at 101 and subtract this calculation at 100. Thanks to the laws of physics and limited size of the chalkboard, I don't have enough room. And I'm going to jump to the next slide. Integrating this out, what they've done here is they went ahead and reduced their fraction. They said, hey, this thing evaluates out to be negative 0.00025 x squared plus 12.2 x from 101, from 100 to 101. And then they just did the algebra, right? They calculated what it was at 101 and subtracted from that the calculation at 100. Came up with 1215. Then the second part of the question asked us to do the same calculation, but from 100 to 110. And the change of profit in that case came out to be $121.48, $121.48. Now, moving ahead, there's another thing we should talk about in terms of the integral, the average value of a function. To explain this idea, I think it'll be easier to show what's happening here. What we've got is a function that looks however it wants to look. We're saying, what's the area from A to B here? This is going to come out to be A. This is the integral from A to B of your function x dx. This is your function of x. Now, we know this isn't the case, but if it were a box, if it was just something like this, the area would just be the length times the height. So it would have constant height all the way through, right? So looking at this, if we were to take and divide our integral from A to B of our function, divide that by the length, that's like saying, if our function was constant, what would that value be? Another way to think of it is, it's saying what's the average value, the average height of our function. Make sense what I mean? Folks at home, does that make sense?
Yeah.
Yeah, cool, awesome. Well, the average of a function the average value of a function on A to B is 1 over b minus a times the integral from a to b of your function evaluated with respect to x. And the whole idea is saying, if this thing was a box, then what would the height be? And that's the same question as what's the average value of your function on this interval? This might become a little bit more clear down the road for anybody who's looking at it like, what? And the reason why it'll be more clear is I have a better definition for what this definite integral is doing that I'm going to use. I think this other definition really clarifies the whole idea of how this thing gets the area. So, having said all this, one application might be to find the average cost per unit of a product. So if the function of cost changes with time, so what I mean to say is if we have something that looks like this, cost as a function of time is equal to, they really love their decimals in this book. Plus 13.5, 13.15, yeah, 15. Over a period of 2 years. So what this is doing, what this function is saying is, in the case of this problem, you've got CD players that their cost can be modeled as a function of time. And the data that leads to this model, well, that data was gathered over a period of 2 years. So we've got a function of the cost of a CD player. We've got a function of time representing the cost of a CD player, is what I'm trying to say. Now, what we want to find is the average cost of this CD player in that 2-year period. So what we're going to do is we're going to integrate from 0 to 24 our cost function with respect to time. We're going to divide this whole thing by the length of that period of time. This is going to tell us the average cost. So looking at what's happening, we've got our cost function, we're finding the area underneath it, and dividing it by the length of time. So we're finding that average functional value. What it's going to come out to be is 14.23. Now again, because of room, and time constraints, just jumping to this slide and explaining it. What we're going to have is the integral from 0 to 24 of our cost function integrated with respect to time, all of this divided by 1 over 24. Now this 1 over 24, it's b minus a. That's all it is. Since a was 0 and b was 24, it's going to come out to be 1 over 24, right? Now, integrating all of this, just like we normally would, then applying our bounds, we get 1/24 times whatever this thing calculates out to be from 0 to 24, which in this case happens to be 341.52. That value divided by 24, the average cost comes out to be $14.23. Now, before we go any further, there are two classes of functions that are going to be good to know about. Even and odd functions. An even function is a function that when you put in a negative x value, it's equal to as if you just put in the normal x value. An odd function is going to be a little bit different. So this is even. This is odd. Odd is going to be the case where the negative of your function evaluated x is equal to your function evaluated at negative x. What does this definition mean? What do these things look like? Well, two common examples. X squared is an even function. X cubed is an odd function. So what we're talking about is a form of symmetry. Even functions are symmetric across the y-axis. Odd functions, you have to take the reflection across the x-axis and then the reflection across the y-axis and then the reflection across the x-axis. There's a bunch of other examples, but generally why these are called even and odd, it actually has to do with expansions in which terms come out. In even functions, you have cosine terms, which are even terms. And then in odd functions, you have sine terms, which are odd terms. And this is all because of what's called Fourier expansion, which is not something you'll have to worry about in this class. That doesn't show up till much later in math. But the reason why we point it out now, this idea of even and odd function, is because if we were to integrate from A to A, or from negative A to A, and our odd function, look what happens. We've got negative area down here. We've got positive area up here. But they're equal area. So the integral from negative A to A of an odd function is going to be 0. Meanwhile, the integral of an even function from negative A to A It'd be double if you had just said from 0 to a. So the reason why this is worth noting is because, well, you can save yourself a headache sometimes. It's usually pretty nice to evaluate at 0. So if we can do that, let's do that. And if we can recognize, hey, this thing's odd, so it's just gonna integrate out to be 0, well, that's convenient too. But again, it's based off of integrating in a symmetric way, from negative a to a. So an example of this, 2 examples. -2 to 2 of x to the 4th Now let's use x squared. That'll be nicer. X squared. We're integrating with respect to x. This thing is going to come out to be 1/3 x to the 3rd -2 to 2. Uh-oh. Oh, I don't want to say it like that. What we're going to have here is going to be 1/3 x, or my mistake, 2 to the 3rd minus 1/3 -2 to the 3rd. Well, this thing is going to come out to be 1/3 8 minus 1/3 -8, right? Well, this is just going to be adding 1/3 8 again, right? So what I'm saying is, this is what we're going to get. And this we can rewrite as 2/3 times 8, or 16/3. That was a lot of work to get to that. If, however, we said, this function's even, x squared, we just said it was. It's nice and symmetric about the y-axis, right? So if we said that, hey, I don't need to do all of this. What I need to do is I need to make this math easier for me to work with. This is going to be equal to 2 times the integral 0 to 2 of x squared dx. Okay, so far most of this is going to look the same, isn't it? I have 1/3 x to the 3rd, but now evaluated from 0 to 2. Well, this thing evaluated at 0, it's just going to be 0. So what we've got is 2 times 1/3, 2 to the 3rd. And a lot less work. A whole hell of a lot less work. So it saves us on the back end with the algebra, recognizing these odd and even functions. And that's why we point them out now. So as another example, we're going to use pretty much the exact same problem, except now we're going to say x to the 3rd power. this is gonna come out to be 1/4 x to the fourth from -2 to 2. This is going to evaluate out to be 1/4 x evaluated at 2 raised to the fourth power minus 1/4 x evaluated at -2 to the fourth power. So this is going to come out to be 1/4 times 16 minus 1/4 times 16. Right? Well, this is just 0. Did all that work just to get 0. But if I had noticed instead that, hey, x to the third, that thing's an odd function. Since it's odd, it's automatically going to be 0, as long as we integrate from -a to a, right? So tricks of the trade, knowing odd and even functions help you reduce some of the math. It's really convenient.
So does that exponent normally correlate to whether or not it's odd or even?
That's a good question. Play with it. Graph a bunch of polynomials and play with them. See what happens. Because that is a great question. And I think it'll answer your question a little bit. You'll find some cool patterns that pop up. Having said all of this, I didn't realize they used the exact same example. That's funny. Okay, well, since we don't have enough time to go over another problem, I'm gonna let y'all go. If y'all have any questions, I'll stick around for a little bit, but y'all are free to leave. Have a good one, everybody.